Hey guys, welcome back to Food for Thought Physics, where today we're going to be using our knowledge of vectors to solve this example problem in 2D. So I'm rowing a boat across a 20-meter wide river. I can row my boat at a constant 5 meters per second, and the river moves at a constant 3 meters per second, parallel to the shore. Now before solving any of these questions here, the first thing we should do is set up a pair of coordinate axes. And you can see I've somewhat drawn this river here. So we see, well, a nice pair of axes would be if we set one just the direction across the river and the other as parallel to the river, because that forms a nice 90-degree angle here, so they're perpendicular. And I'm going to say that this parallel direction is the x direction, and the across direction is going to be the y direction. So now we can look at this. Well, if I row perpendicular to the shore, how long will it take me to get across? Well, we know that I can row at 5 meters per second, so I can draw my velocity vector, say I'm starting here, as a arrow pointing straight across the river, straight in the y direction, with a magnitude of 5 meters per second. So I'm going to say this is 5 meters per second. And we know, well, the river is also moving at 3 meters per second parallel to the shore. Or rather, the water is. So that'll be going in only the x direction, parallel to the parallel direction. And the magnitude of this vector here is going to be 3 meters per second. So now, well, we can add these two vectors together because we know, well, my boat is going to be moving in this direction, while the water is also going to be carrying me in this direction with these two magnitudes. So we can imagine our net velocity of our boat as we sail straight across, or as we row straight across the river, is going to actually be this green vector here, pointing in this direction. So now, well, let's see. If I row perpendicular to the shore, how long will it take me to get across? Well, due to these two axes being perpendicular, we know that the x and y components of these vectors are all going to be independent. So that means that this water, this 3 meters per second, right now doesn't actually matter, because we know that in the y direction, our velocity is 5 meters per second, and we know we need to go 20 total meters in the y direction. I'm going to draw that here. This is 20 meters, as it says up there. So we need to go 20 meters in the y direction, and we're moving at 5 meters per second in the y direction. So we can just divide 20 by 5 and get 4 seconds. Now, how far downstream will I end up? Well, again, this y velocity now doesn't affect the x velocity. We want to see how far in the x direction will we end up. Well, if we're going for 4 seconds, and every second we move 3 meters more in the x direction, then we just multiply those together, and we get 12 meters. So we end up 12 meters downstream of our original position. So we would end up at this position, but 12 meters further downstream because the river was going to carry us that far. So now, what angle should I row at to get straight across to the opposite bank? Well, I'm going to actually move my diagram over here. I'm going to draw a new one here, say. So how would that happen? Well, what angle should I row at to get straight across to the opposite bank? Well, if you can imagine, if I row in this direction, some random direction this way, at 5 meters per second, and then the water carries me 3 meters per second in this direction, then you can imagine there is some angle such that once I do it, then the net velocity is actually going to be straight in the y direction, so that I end up straight across the river. So what is this angle exactly? Let's see. We can make this triangle here, and since we know the water is moving in the x direction and our net velocity at the end should be in the y direction, then we know this here is a right angle. And we also know the magnitude of this black vector over here, our velocity, that's going to be 5 meters per second, while the velocity of the water here is going to be 3 meters per second. And if we can find this angle over here, call it theta, by just doing something like theta equals the inverse sine of 3/5. Because we know, well, sine of that angle there, of this theta, is going to be 3 over 5, because this is a right triangle. So we can take the inverse sine of 3/5 to find theta, And then we can simply take 90 degrees minus theta in order to get this angle right here, which is the desired angle, the angle relative to the shore. So we can compute this with our calculator. We get theta is approximately 36.9 degrees, which means the desired angle, which we can imagine as this angle relative to the shore, is going to be about 53.1 degrees. And how long does this journey take? Well, again, we see this right triangle here. We know the hypotenuse is 5 and one of the legs is 3, so then we can determine, well, that means the other leg must be 4. So this net velocity here is going to be 4 meters per second in the y direction. And we want to go 20 in the y direction. So that's just going to take 5 seconds, because 20 divided by 4 is 5. So this river sailing problem is actually somewhat a common problem in introductory physics. You'll see these things where we have some velocity and the river is moving at some velocity, and we are trying to get across either at a straight, we are trying to either get straight across or at some angle, and we need to compute certain things. So yes, this is somewhat a commonly used example to demonstrate vectors. So now in the next video, we're going to look at a special type of 2D motion, actually, which is known as projectile motion. And projectile motion is basically going to involve firing projectiles at some angle relative to the surface of the Earth, and looking at the motion of those projectiles.